All right, I think today, as I said in the Slack, we're going to talk about this so-called sensible contracts. So first, we talk about some of the background, why this came to be. And it's also, I think, one of the, to me, it's one of the remaining biggest challenge in the BSV space. How do you backtrack without pushing all the historical transactions? So I think that's what Attila has been trying to attack these days, and I've been thinking about this maybe for a year now. So there's no final solution yet. So today I want to introduce the problem and then how a sensible contract deal with it, and then hopefully we can have more live discussions, brainstorming, and maybe somebody, either one of us came up with a solution or somebody else who's watching this, they can know this is the problem. It's not even $1 million problem. It's like $1 billion problem. So it's anybody who's watching. So if you have a solution, let us know. So, all right, let's get started. So let me share my screen. You guys see this okay? Let me.
Yep.
Let me do this.
On my end, I can.
Let me do it again on this screen so I can look into the camera. Okay, we just lost Attila. I think it's coming back. Maybe it's in the mall.
Yeah, he said he was in a public area where they didn't have the best silence and Wi-Fi, so hopefully he can come back.
Let me also open the sensible. You guys heard about sensible?
I saw that you posted it, and then I was too busy working on a bunch of other things and catching up on old posts that I couldn't. Okay. I read this page, but I'm just gonna try and stay as silent as possible because I just don't understand any of it.
Okay. Yeah, it's been around for I think almost 2 years. So it's a big ecosystem. But I think today I'm not going to cover the details, but mostly how it relates to our issue, the issue we are talking about today. Let me ping Attila.
Is it kind of related to being able to save you remember a long time ago, I don't know if you guys remember, but I was asking about how do you save the kind of like the location of the last contract call. I don't want to interrupt again, so I'm just gonna stay silent, but I'll read it while you're trying to connect.
Okay. Mr. Attila, where are you? I think, yeah, let's keep going. I think he probably knows the background, so he can join back later. That's okay. So right. Remember, like, it's almost, it's 2020. We published an article basically saying how do you do purely minor enforced so-called layer 1 tokens, and it's based on UTXO. So basically, all the UTXO, each UTXO, it contains like a tokens. It's almost like contains satoshis, and each such UTXO is independent from all other such token UTXOs. So what's the benefit? So then you can process them independently, right? Let's say, unlike an Ethereum model, right? You have a common shared state. So if you have a token, let's say Alice has some token, B has the same token, then if Alice transfers, it will impact B's transfer. So that means you cannot parallelly process them. First, the UTXO is like independent, right? So if A has its own UTXO, contain his tokens, and B has its own, then they can transfer like separately. There's no interference between each other. Okay, I think he
doesn't get bottlenecked.
I think now he tries to join. Okay, it's back. Hello, you back?
think he's connecting. I see him.
Okay,
Yeah, sorry about that, bad connection.
it's okay. Okay, so we're just, I think this background you probably already know, so I'll just quickly go through what's the background, how the issue came to be. So basically, once we want to do this peer-to-peer token, that's purely UTXO based and minor enforceable at layer 1, we have some issues. Basically, you have two types of attacks that the attackers can fake the token. Because if you receive a token, right, how do you know it's legit? You have to check, right? How do you check? I mean, if you don't do any special trick, you have to go all the way, right? Because the token, once you issue one, you unless you trace all the way back, you don't know whether it's legit, right? The only way you anchor it is have this genesis, almost like a genesis issuance transaction, right? So how do you know it derives from it? You have to go back, right? Because if you don't go back, other people once they can so-called replay attack it. Basically, they issue the same code, but it's a different chain of transactions. So when you see this transaction, you cannot tell. This is only legit, right? But if you resist this one, you don't trace back, you can also be tricked, right, into thinking this is also a legit one, because from the appearance of it, from the last transaction alone, you cannot tell, right? These two are the same, look at the same. And same for here, you can also, you don't even like go from the beginning, you can just, from anywhere in between, you can intercept this, and then from there on, you create like a fake chain of transactions. And then this one, you can also not tell from the one above, right? So that introduces a problem. You have to trace back. But how do you trace back? One thing that, right, is very naive. I think I think a lot of people have come up with this idea. So basically you put, when you transfer the token, the last transaction, but also you give out the whole history. But then there's a scaling problem, right? What if, this token change hands, like 1 million times, right? You don't want a user who has a mobile phone has to go back and trace all this 1 million transactions. That's just not practical. So we came up with a solution here based on so-called induction, mathematical induction, right? So basically the basic idea is you have to trace back to your parent and to your parent's parent. So if you make sure your parent is legit and your grandparent is legit, and then you can, by deduction, the chain of transaction is all legit, because you don't have to go back all the way, right? Because I try to use induction example here. Basically, if you see this transaction, its parent is good. But if its parent is good, that means its parent's parent is also good. So keep going until you hit the issuance transaction, right? So that's how I came up to be. I mean, you can play with the idea, but here's a counter example, right? So for example, if somebody tries to fake a new chain, the third span will fail because, the parent's parent is not good, right? So it will not be valid. So that's the simplest idea to understand how to see this using induction intuitively. But the code is also very straightforward. Basically, you check, we have the all push transaction technique, right? So with that, you can know the parent transaction because all the out point in the pre-image. So you can push the parent transaction, then you can parse it, right? Also, you can parse it in script, and you can see. So when I say whether the parent and the parents is legit, the way we do it is very simple. You look at the script part, right? You look at the locking script part to see if it's the same pattern. Because if it's the same pattern, then okay, this does not come from some fake chain of transactions. So basically, this what it does is you push this transaction in, you also push the parents. So you can parse it and you can compare the script part to see if the same pattern. So this is the basic idea. And then by using induction, we know if this contract is validated and put on chain, you can know for sure without going back all the way that this token is what token UTXO is what you expected. Any questions so far? I think this may be a lot of information here, so I just pause here. Anything? Comments?
I know a little bit about induction from a book, a logic book that I read, where it's kind of like you give a bunch of examples of, I'd have to read it, but I don't know exactly what induction means. So I'm gonna have to look up that definition again.
I think let's give one simple example, right? So let's say you want to compute, for example. Let's say you want to compute all the natural numbers adding up to n, right? Just give one example. Well, how do you compute it? One way is, of course, you add them one by one, right? Then you add n times. But the other way, using induction, is also assume now you already solved the problem, but for a smaller problem, right? Instead of Pn, which is the sum of all the number from 0 to n, you now know Pn minus 1. Then how do you get, if you know Pn minus 1, how do you compute Pn? You only have to add the last one, right? So this is the basic induction idea we all learn from, like, I don't know, like high school or middle school. I kind of forget, yeah. Also, another one is the Fibonacci array, right? So basically, you have if you have two rabbits, and by the end they have another one baby rabbit, and then you keep going every year. The sum is of the previous 2 years. So that's also induction. Right? So basically, you first solve the smaller problem. It's kind of like a recursion in computer science domain, right? So if you solve the smaller problem, you can solve using it as a base to solve a bigger problem.
I'll just jump in there. In the specific example for us, the base case is the minting event. When you mint a new token, you take the out point that the contract was deployed to, and you embed that carrying forward. So that's the issuance TXID. So that's the base case, right? That's the case where n equals 0. And then the inductive step is to show that for any given transaction in this sequence, if you can show that it's valid because its parent's parent is valid, then by the principle of induction, you can show that the entire regression, the recursive relationship holds, meaning that the only way someone could spend the transaction is one of two situations. One, they're either minting an authentic fresh token, or B, it is child of a token that eventually was of a valid minting type. That's the inductive step. If we can prove that, that means then you could have tokens that don't need an indexer, that users on Reddit or Telegram could just exchange tokens between themselves, and then looking just at the data of the token and an SPV proof to make sure it's on chain, you could tell immediately it's authentic, that it wasn't forged. It's the real NFT. You don't need a backend to tell you. You don't need to index the entire chain of spends for the NFT or the tokens. You just know that it's valid because of the, you know the contract code, and you know the inductive step holds.
Correct. Absolutely. Yes, that's why I call it the billion-dollar question, because you can solve this. That's like you open up a completely new paradigm of smart contract on Bitcoin. So I just introduced the solution, one solution here, but looks great, right? Because when I first wrote it, I think it works, so I'm very glad. But then it turns out a lot of people piling up. I think even, let's say if they have comments here. So
I was just gonna say too, I was looking up and I found that portion of the logic book where it talks about inductive versus deductive logic. And they didn't want to interrupt too much, but I was just gonna, I'll give you guys the book, and so you know what I.
Okay. Yeah.
I mean, it kind of makes sense to me, but I don't know exactly. It's just like when you do deductive logic, you're taking premises that you're accepting as being true, and you're following from that. But when you're doing an inductive logic, then you're giving examples that are showing that it's extremely probable, but it's not. I have to reread the book, so I'm just going to put it in the Slack after. Maybe you could put it in the YouTube show notes.
Okay, yeah, I would do. So basically, the this looks like a promising problem, but that's one inherent drawback. What is that? So basically, this is the current transaction, right? So if you want to verify the parents, this is good. You have to push the transaction into, when you have to, as I said, right, using the push transaction technique, you only have the transaction ID, the out point. So how do you know is a original transaction? You have to push it and then hash it to match the transaction ID, right? But here's the issue, right? Again, using the induction idea. So let's say the size of this is transaction, let's say is the size is S3, right? So approximately, because you have to add in the unlocking script in the input, you have to put this transaction 2 and transaction 1 into it. So approximately this transaction size is at least, right, the size of transaction 1 plus 2, right? So if you notice, as I said earlier, we have this Fibonacci series. It actually grows almost like exponentially, because if you imagine, right, you have 2 at the beginning, then you have 4, and then you have 6, you have 10. It's just, you can, in theory, this one works, but the practical issue is the transaction size just grows. I think it's almost like either exponentially or super exponentially. That means
Fibonacci is, sorry to interrupt, Fibonacci sequence is exponential.
Exponential. Okay, good. So basically, that in practice, you'll hear this issue after you spend a few times. You'll hit the bottleneck. You cannot even spend it because the size of the transaction will exceed what the mining network enforce the limit. So that's why there are a few folks that try to propose different solutions. I think one of the most famous one I have known is the so-called sensible contract. I think it's a huge suite of tools and libraries, middleware. I think today I just focus on that sensible on how they solve this issue. So if we go to the white paper, so you can download it from the white paper section. They have the PDF over here. You can download it from there. So basically, how do they solve it? So first, if you look at the white paper, I think, so basically this is our current transaction contract, because using the push transaction technique, then we can get all the outputs, right? So we can enforce how does the contract evolve in the future. But we have some issues, right? As they put in this graph, we can kind of have some difficulty backtracking all the way, because if you want to do that, if you push all the history, then because the history grows, right? And as Tila just mentioned, it actually grows at exponential rate. It's just not practical if the chain of transactions just keep growing, right? So we focus on this part. So if you really want to solve the problem, what is so I think the crucial part for here, we have to know the script for the parents transaction. That's the only part we care, because the parents script, right, we know from the pre-image, right? It's part of the pre-image. If we can go back. So this is a pre-image, right? For people who have not seen this. So the fifth part, the script code, this is the locking script from the parent transaction. So that part we know. The only thing we don't know is the parents script code. So that's what we want to know. So I think the original proposal I have, the peer-to-peer token one, you can know it, but you have to push the parents and parents transaction, which have this bloating transaction size issue. So they try to get around it using two approaches. One is, if you cannot solve it right directly, we have to get around. So why not we just have somebody verify this off chain, and then they sign it. It's almost like Oracle, right? So if you don't know the data, you just import it from off chain, and then how do you know it's you want to trust it? You have somebody, hopefully it's a trustworthy Oracle, signs it with his public key, and then you can verify if it is signed. If it's signed, then you trust it. Then you trust it, you can know map from from because you know the UTXOs for here, so you can map it to the script code. You can know for sure this one is the one you are looking for. So once you have so basically what it does, I think let's skip to the part. So basically what do they sign? They sign this turbo here. So basically this is the out point, right? And this is the UTXO ID, basically. Transaction ID and output index, the UTXO is Z. And then this is the value, how many Satoshis contains, and this is the script code, basically the locking script in the output, right? So Bitcoin is transaction output, right? Two parts. The Satoshi bound part, the value is contained in the value, and also the locking script part, which they call script code. So if you sign this, if I can compare, if I now know because I know the parent's transaction ID, actually they sign another field. This you can think about the parent ID. If you know the parent ID, you can know, oh, which UTXO I'm spending from. So then you can, from this transaction ID, it's almost like a hash table, right? You can look up what is the parents, because this is the parents transaction ID. So you can know what's the script code in the parents. So that's how they get around this issue. So basically you either solve it in script, right? On chain, or you can outsource this to external parties. So they solve it, they verify this is true, then assign it, you put in, you import in the contract, you verify the signature is correct, then you can trust this data. So it allows you to map from the transaction ID of the parent to the parent's script code. And then once you have this, that's the only thing we need, right? So once you have this, you can compare with the current script code. You can see it's the same pattern, then you know by deduction, right? It's all good. Any questions so far here?
Did you mean induction or deduction?
Induction. It's all induction here.
And induction. Okay, yeah, induction.
Yeah, it's all
that's what
induction.
I thought would be right. Yeah, I think one of the things that I was thinking about when you were describing this whole problem was the idea of kind of what we do with what Bitcoin itself does, which is especially with pruning in order to save space, is that everybody gets a copy of the chain of transactions. And I don't want to mess this up because it's complicated, but the SPV thing, you know, where you store all the headers and on your wallet, and then you know that if somebody goes and changes the history, then something has changed, but you're not actually storing all the transactions. And so in a similar way, maybe there's something, if we're doing it with tokens, because you're trying to, you know, validate that nobody's changing history. And so we're trying to, you know, grab a few here and there to kind of use induction to see if something has changed or not. But if there's a way of just really efficiently storing just the chain of all the hash headers, then you would know that it has never changed. So then you could pick one out here or there or something. That was just something I wanted to add, that maybe you could look at that architecture of how they solved it in Bitcoin itself.
I'll add on to that. Like, that's an interesting idea of using kind of like a Merkle tree structure in the history. And I think it's definitely needs more exploration. I think there's something there with Merkle tree. The thing is, it's not that the history was changed. It's that there could be a forgery, and in which case there could be like a forged lineage, which is unchanged. So in this case, it's not that the history was changed. It's that the user injects the red box and it's immutable. It's a valid transaction on the Bitcoin network, but it's not valid in the token overlay. The token overlay is false because it doesn't come from the original minting. I like the idea of using something with block headers and Merkle trees. I have like a whole side exploration. So I think you're onto something there. But in this case, the induction step is to make it so that you have like it's literally unspendable if it didn't come from that lineage. And in this case, it could still be forged.
Got it. Okay, cool. I'll read it over more. I don't understand it.
I'd like to highlight something because this kind of came into sharp focus for me when I was reading BCH's cache tokens. So they have something called cache token, and they're actually proposing a change to the virtual machine to basically compress the unlocking script into a hash. And the way they're doing it, I'll just quickly summarize, is instead of having the entire unlocking script form the TXID, they're basically double hashing the unlocking script and then signing that hash. And so then they can like discard the unlocking script. So then you don't have this issue where you have to keep supplying the parent TX, and then you get that exponential growth, because once you include the parent TX, then you spend it again. Now it includes the previous parent, and then it explodes. That's what cache token's doing, is this concept of moving into a detached signatures. So you have the compressed hash representing the parent. So what the reason they're doing it is because they also need the grandparent transaction ID, and they need to know the contents of the grandparent, because they need to verify that a locking script is equal to the input script code of the current context, because that's the final, that's like closing the loop in that inductive step. So what we really are after here, there's a nice diagram here. What we really want is this grandparent TX, and to know that it matches what's in the current pre-image. That's what we're all after, is that grandparent, and then being able to link the output that was spent in the grandparent to the TXID of the grandparent, and making sure that was in the sig hash pre-image. That's the loop. If we can close that, we have something, if you say $1 billion solution, it's really, I think it's the $1 trillion question. So anyways, I just want to share that. That's what we're really after, is to reduce this bloat here, where the grandparent TX has to like keep snowballing it. And this is how cache tokens did it with the hash. It's a consensus change to move to a new transaction format, which is pretty heavy.
It's this big deal. It's like Ready Player One.
Yeah.
$500 billion.
Metaverse.
Yeah.
So Attila, do you understand how I think they try to use a similar idea. I don't know whether they read an article or something. I don't know. They have independent train of thought reaching the same conclusion, but this seems I wouldn't say the only, at least the only solution I'm looking. I know how do you solve. Basically, you don't have to go all the way back. You only have to go back maybe 1 or 2 steps at the most, right? So how does this compress here? How can you say? I think you should just quickly go over.
Sure. Yes.
Not
okay.
Quite. So they change the way they calculate transaction ID or something, or
exactly what they're doing is, instead of taking the inputs, the locking script, they're hashing that up front, and then only signing the hash of the inputs in the transaction, so that the signatures can be discarded, and the unlocking script can be discarded. So then you can feed in the parent transaction, and you basically discarded all the stuff that you basically don't end up bloating and compounding, because you end up discarding the parent raw TXs, because it's kind of like a
I know. Segregate waitlist.
They actually compare it to seg witness. Exactly. It's using detached signatures, and then that hash on the right diagram, the right picture, that's a witness signature, and that's what they called it at first, was a witness.
They don't hash the whole thing, right? They just maybe hash, I don't know. Get rid of the input.
Correct. They basically take the hash of the inputs basically, and then discard the rest. Yep. And then what they do in the ASM code that they provided with their BCH opcode set is they reconstruct the parent in the parent, and then ultimately the grandparent, and then compare it. They also have the covenant technique, which is the op push TX, but they're all doing it like assembly style, right? But there's working code there that uses this, but and they also have the exponential growth problem, and that's why they realize they need to have this detached signatures, or SegWit, for the inputs, and that's their solution. They call it PMV3.
Okay. Yeah, I think after you share a brief look at it, it's almost like we almost reached the same point, but I don't know whether they read our solutions first, or they came up with this independent. But it seems like this is a recurring scheme. If you want to do like not only tokens, because back tracing can be used for a lot of other scenarios as well. Right? The token is maybe just one of them. If you have this technique, you can use it across all the different contracts. I think that's why at the beginning, sensible, they call it sensible token, but then they notice once you have the backtracking problem solved, you can then actually, it's not only for token, you can for any arbitrary smart contract. So going back to here, they propose two solutions, right? You have, go ahead.
Do you mind just giving a brief background on the the contract backward tracing? Just shortly. If that's
Yeah, coming back.
I think I missed some part. Yeah.
Yeah. So so want to highlight this again. Basically, what's the problem here? So let's say you have a token A, right? So you have a UTXO based tokens. So now you transfer it, keep going, right? So if you want to use it in a peer-to-peer way, so this is the current, the latest, the chain at the tip of the chain, right? So this is your, let's say, Samir's token, right? So what if you want to transfer it to Attila in peer-to-peer way? You only want to transfer this transaction, right? You give it, it's like giving Bitcoins, right? Native Bitcoins, you give it to Attila. But how does Attila verify this? If you don't do anything, he has to go through all the way back, right? Because otherwise you have two types of attacks, right? You can either issue the same, appearance, looking the same, either this way or this way, because at the end, right, you can fake another chain of tokens, right? So in the end, this transaction will look almost the same, right? With this one, you don't know whether Attila give you the authentic. No, from Attila's point of view, you don't know Samir's give you the authentic token or is giving the fake one or the fake two, right? You don't know. So the only way you can know for sure is you have to give the whole transaction history, right? But then that's not very good for peer-to-peer, right? Because you may change it by like 1 million times.
Yeah, the SPV solves for the UTXO, right? The Markov proof and the headers. So when I'm giving my token to Attila, doesn't it trigger another transaction, which also again has the same Markov proof and SPV, the header validation. So when you're saying giving the money, it's not outside the Bitcoin, right? It's still part of the Bitcoin UTXO. Isn't that right?
Yeah. So here's the issue, right? So what for SPV or all these chain headers, this can only ensure that transaction is valid, right? This, if you look at the graph, I want to emphasize all these are legit transactions in terms of for Bitcoin network. This is all legit, but as Attila said, right, token is almost like it's not like a native crypto native currency for the native asset for the Bitcoin blockchain, because only Satoshi is native, right? Then the token is almost like an overlay, or you can call it a second-class citizen. So the miners only look at the transaction, make sure the Satoshi's rules are fine, but it doesn't guarantee you the token rules are, they don't enforce the token rules. So that's why even these are all valid Bitcoin transactions, right? You can have the valid Merkle proof, you can have it's a chain to it's mined. This is all good, right? But that doesn't mean even it's a valid Bitcoin transaction, it doesn't mean it's a valid token transaction. Does that make sense? Because token is kind of like a second layer or overlay asset here.
Yeah, I think that makes sense. Just the thought that when you're sending the transaction over, we're still going to have, we can attach it to a new UTXO transaction model, right? So it has to go through, because when you're just giving the tokens to somebody else, that doesn't mean I'm just giving the token. It has to tie back to all the, it has to go through the transactions of, say, a new UTXO, which is again has to be mined with the Bitcoin block, the miners and everything. So the miner fees, it's going to attach to this new token. So I honestly don't see the, but I think this is a big issue right now. But I kind of still trying to figure out why there is a problem and not use the current SPV model itself to figure this out.
Here's another note on it. SPV works for this. So you see the red box here, that is a valid transaction, and you will have a valid SPV proof. So the UTXO was mined. It is a valid transaction, because think of it like this. In a chain of spends, you can go to what's on chain or any block explorer, and you can copy paste the output of anything right now. And then you can copy that and paste it into any fresh transaction, right? It's just data. So you can take literally anything on the blockchain, copy paste it, and then rebroadcast it as a new fresh TX, right? So now to spend that, anyone can spend that as well. So then the way to enforce these, how I say, copy paste protection, is to do the induction proof, so that no one else could own that UTXO unless they had the parent and the grandparent that came from the legit minting event. It's like saying having an NFT where you can copy paste your favorite dog NFT onto the blockchain and say, hey, look, I have an NFT, it's authentic. But if you use this technique, if we solve this induction proof, you literally couldn't use that copy paste technique, because you would actually be unable to spend the UTXO at layer 1. So you couldn't have these fake coins copy pasted, because the principle of induction would guarantee that it truly is like unique. And since we don't have that yet, at any point you can just copy, any intermediate transaction, and hence the red box, and then spoof a chain. And users, the only way they know that they have the real thing is they have to go back to Genesis, which could be millions of transfers. So this isn't very good for exchanging tokens on a website or a community forum, because what, you're going to pass around 1 million transactions every time someone buys it? No, that's not very good. Ideally, you just pass the latest one, and by the principle of mathematical induction, you're able to guarantee that this could not have been physically copy pasted, because the mathematics prohibits that from being possible in the first place. That's the $1 billion problem that we want solved.
Yeah, I have to give it a little bit of thought, but
Yeah.
it just feels like the solutions is within here. But yeah. But I'll give more thoughts, and then
Okay.
probably we can have another
Yeah,
conversation.
here-
But thank you guys.
Okay, no problem. I know it's not like a $1,000 problem. That's why it's not very easy to follow, to say the least, right? So basically here, right, we propose a solution. It looks fine, but then in reality, it has this transaction size exploding issue. That's why Sensible have proposed, right? Either you do you kind of like offload some computation, the bloating part off chain, to do it by some oracle, and then you trust you can import it. Or this is controversial, you can also change the transaction format, right? More specifically, you can change the pre-image format so that you can contain this information in a new pre-image format. I think that's what also the BCH is trying to do with this. But they also propose another way, but you don't change the transaction ID format, you just change the transaction pre-image format. But it's very similar, I would say. But that part, I mean, for us, because we want to make sure that the protocol is set in stone, right? We're not like a BCH. Anybody who has any new use case, they just change the consensus, either add opcode or change even transaction format or pre-image format. Yeah, that's why they propose two. They implement the first one, because that doesn't require any consensus change. So they call it a signature service. So the good part about this, it is an oracle, but it involves less trust, because all the data is signed its own chain, right? You're just basically signed, if given this transaction, give this ID, output ID, this is the balance, and also this is the script, and also this the next transaction spends it. Everything is open. You can check yourself, right? It's not like publishing some price or weather data, right? There's no way for you to independently check. So that's the benefit. It's kind of oracle, but you have involved less trust, because the data is coming from the blockchain itself. As for the second part, I think they propose this. Basically, you add some field to the pre-image that contains the parent transaction script. That's you have to change the consensus part, which is not implemented.
Just to
Yeah.
help define. Okay, go ahead.
Sorry, what they're saying is add the hash of the data outs of the parent and the parent's parent to the pre-image, because then you could reconstruct what the other outputs were just from the hash. So they're kind of doing that, basically information compression as well. It's just another way of us indirectly getting at the same hash that they're basically just saying detach the signatures. I think this is a lot more elegant. What Sensible's proposing is we just add 2 extra fields to take the hash of the data outs and then put them in there.
Mhm.
I'd like to ask a
Sure.
question. I'd like to go back to the first solution they have. I don't quite fully understand the Oracle solution, and maybe it'll also help others to understand how they've implemented it. When you say there's trust involved, what's the nature of the trust? Like, can the Oracle, in theory, sign something that's completely like fake? What is the nature of that trust? Like, and where is this signature used? Is it, we pass it into the unlocking script each time? And does the code verify that the parent and the parent signatures match? What does an attack look like? I'm just curious what an attack could look like if the Oracle faked something. I'm not quite understanding what that is.
Yeah, good you bring up this. So that's actually, I wrote an article about, I think last week about this. So actually, I even proposed a solution for this. So if you go to the sCrypt official Medium blog, we have this article called Smart Contract Based Oracle Slashing. So what does it mean? So as I said, right, because ideal, what do you want here? You want to, because you know that from the pre-image, you know the previous transaction ID, right? Because that's the parent, right? You know that. You want to know from this, you want to derive the locking script from the parent's parent, right? How do you do it natively? You have to put not only the parent transaction, you have to push the parent's parent, and then you can parse it, right? Then you can get to the script. But that's like too heavy, right? We talk about that in the article, because if you do this, then the transaction size is going to grow exponentially as you transfer the tokens back and forth, right? So what they do is you have the Oracle signs this. What does this mean? This is the UTXO, right? Based on transaction ID and index, uniquely identify the UTXO, right? So this Oracle basically, if it signs this, what does it say? It said, oh, this UTXO has this many Satoshis, and this is the script. And this is the transaction ID that spans the UTXO. That's what the Oracle signs. Basically says, I validate this, trust me. So how does, again, it's almost like a Bitcoin signature, right? Using ECDSA, but the only thing difference here is using different signature scheme called Robin signature, right? So basically uses Robin public key, a private key, signs this data, and inside the contract, right? You validate, it's like any digital signature, right? You can use the message itself, signed, you can use it's a public key and signature, you can verify without knowing the private key, right? But in the smart contract itself, you have to check the signature is valid. Once you valid, I can trust this turbo here, right? And then because I know the transaction ID for my parent, I can get the script here. I don't have to push the whole transaction and parse it. I can just get it. It's almost like a lookup, like a reverse lookup, right? I can know this is good. I can just fetch this. Questions?
One of the things I wanted to say a little bit further back was just to how to define this problem from a really high level. And I was trying to do it for Samir just to frame the problem. And I was saying that it's like, because I keep right next to me, and I was looking at this, I keep a big pile of all the currencies that I've gathered from my travels. And everybody has a different way of, making sure that it's a legitimate cash. So if I give $1, let me just grab it so I can just show you. But there's like on the dollar bill, there's like all these little things. There's the little owl in the corner, and you can say like, is this a real dollar bill? or is this not, right? So all of these currencies, this, right, this it, but like this one is pretty easy to fake, and you could feel it, and it's just like, you know, it's just like a piece of crap. But some of these, like the Australian one, is made out of plastic, and you see how it has all these little things in it. So as when you're the person at the cashier, you can grab this, and you know, like if you do $100 bill, they're going to, you know, they're going to take it and they're going to hold it up to the light, and they're going to check a few things to make sure that it's legit. So the same thing is true. Like here, this looks like it's really cool, and I use it as like a symbol, but it's all fake, right? So it's not going to work. So anyways, the problem here is that there's a bunch of people that are trying to design these tokens that you're building on top of Bitcoin SV. We're not using the native Satoshis, but we're building tokens on top. And just like there's all these countries that are competing, trying to build their own currency that can't be spoofed, there's a bunch of people that are competing, trying to build a protocol that is efficient, so you can just hand them the dollar bill. You don't have to go and look it up and look at all the registry. You just want to make sure, can I inductively, just by looking at a few characteristics, is this legit or is this counterfeit? That's sort of my interpretation, and from a very high level. And
I think kind of understand that point now. So again, going back to the SPV, right? So that token is still attached with a rope to the Bitcoin, you know, via the SPV and the proof. The token in itself, there's the UTXO, and there's this other layer, another addition of another layer of, say, metadata or whatever. That's the token. So what we are really trying to solve is that if I just transfer that token without this connection, can I still do that? Is that what really we are trying to solve here? Or because I mean, I don't think we can really solve that, or is, because, you know, we have to have a way to connect back to the you know, the Bitcoin. So, and that is via the bridge of UTXO. So whenever I'm moving that token, the token itself, it'll have to be another UTXO that again attaches back to the original, via the SPV and the Merkle proof and all that. So honestly, I don't see there's even a problem here, or yeah.
Another way to look at it is, when you're presented with a UTXO, how do you know it's not just, like, let's say there's a data in there, okay? There's a data field. Let's say this is a token Doge. That's the name.
Yep.
There's a string in there, and Doge 10, and then you receive that. So how do you know that? How do you know from a mathematical sense, a logical sense, that individual UTXO came from the very first unique minting event of Doge, and it wasn't like Alice over there that just minted another UTXO valid
from Shiba Inu.
Right, and then just minted a copy, and then passes that on to you, and so you look at them and you're like, you can't tell without going back in history. Like the analogy that Kevin was giving, where when you look at a paper currency, they tried to make it, I think the term is self-evident, or proof of work, or tamper resistant. So when you look at a token that you received as Doge token, and what you want to be able to do is look at that, and maybe its parent or the grandparent, and then say, yes, this is authentic. But if we don't have an inductive proof, it's not sufficient to look at the current raw TX and the parents. You actually have to go back linearly into the entire chain. And so you can verify that it's authentic going back to exactly the correct minting one, and it didn't, like, say, diverge back, you know, to Alice's where she forged it. So the SPV will tell you that, yeah, these are valid Bitcoin spends, but SPV is not going to tell you that, oh, this lineage is from the forged one from Alice, or this is the actual lineage from the real issuer. And that's what we want to identify.
Yeah. Have you guys looked into Solana's proof of history? I think, have you guys looked into that one? It kind of looks similar to what
they're using a hash chain to basically kind of let's say simulate, but it's kind of like a hash chain for proof of work. And there's interesting stuff there with a hash chain. I don't want to rule it out completely, but a hash chain is like a forward. How do you call it? It's like a forward constraint, and it going backwards. You know, I think what you're saying there is that compressed hash in the PMV3 in a way it really is a hash chain. So yeah, you're right that Solana uses a proof of history, but that's kind of like a forward. I think a forward progression. And I can't say right now it'll help us. I looked into it. I couldn't find anything.
Yeah, from the token problem itself, for me, I honestly don't see that, you know, creating new token is a problem. We can sufficiently with SPV proof, even if we move, but that's only my viewpoint. But you guys are, you know, experts on that, from a technical standpoint. But from a standpoint of where I stand, I think like the token itself, you know, with the SPV proof, whatever you add, we can still be able to sufficiently say that it's a valid token. But again, the proof of history is something what Xiaowei, you mentioned, like, you know, in one of these, it sounds similar to what we are trying to do just for the token itself, just to make sure that the token that I have, without having all these SPV proofs, I can say with that, you know, the proof of history kind of, you know, concept, going back to the hash chain, I should be able to say that, okay, this token is a valid token from going back to the minting, from the point of the minting. That kind of sounds similar to what the solution is. But yeah, I mean, I still need to go back and do some more research. But just based on this presentation, or, you know, from some of my earlier research on sensible contract, I still have some lack of clarity. Then maybe I should say that.
This principle of induction, I don't think it's publicly solved. And if we do solve it, we really get something special. There is a very real problem here. I personally have been thinking about this, and I wrote a lot of stuff on this for at least a year. There's definitely a real problem, because what you really want is constant time verification of the token. We can do linear time. You just index the whole thing and serve it up, and serve a Merkle proof and SPV proof at the tip. Yeah, that works. But the problem is, what do you do when you have a token that's been transferred billions of times? Is every client going to verify that? Are you going to like trust the service to? Now you can reduce the trust, but I think there's suboptimal solutions, especially if we get to like the tera scale. This sensible approach, just to kind of bring it back to what Xiao, you were talking about with this this oracle slashing, I think is interesting, and it does work. And I have a question about the oracle slashing technique, and what the bounty looks like. So is it true that that if someone else can prove a counter proof, then the oracle would then forfeit their bounty?
Yes.
And okay, so that necessarily implies that the NFT that I'm transferring, let's say it's a really cool, you know, some ape of some kind, an ape NFT, and let's say that ape NFT is worth $100 million, then that implies that the bounty for the oracle needs to exceed the value being transferred.
Yes.
I know I'm jumping ahead here, but I want to tie that into the context of the security parameter of this oracle solution is bounded fundamentally by the size of the bounty.
Yes. So basically, if you want to, it's the same with almost like a double spend, right? You know, if you buy a coffee, you probably you don't have to wait, right? Zero-conf works because nobody's going to spend, you know, $1 million just to steal $5, right? Same for here, right? So basically, the cost of cheating has to be bigger than the deposit has to exceed the benefit of cheating, right? Because it's always if it's a rational attacker, if you want to spend X amount, you have the amount you can gain has to be larger than X, right? Same for here. If you put a deposit upfront, that means the maximum gain for your cheating, it has to be lower than this amount, right? For example, you put a bounty. So this high level idea is very simple, right? So it's an oracle, right? So let's say the oracle is a sum oracle, right? Basically, you give it two numbers, you give it the sum, right? X, Y, you give it Z, right? But what if they give you the wrong number, right? What if the oracle sign says, oh, 2.2 equals 5? What do? Then the oracle has to put some bounty upfront saying you have to have X and Y and Z. if you can give me the X plus Y different from the Z I give you, then you have proved, right? I've made the mistake, right? Either intentionally or not, I don't care, right? So if you can prove 2 plus 2 is actually 4, then it's different from 5, right? And then that means I've cheated, and then you take my money, right? So in this way, it's not says it's impossible. Again, everything is economic here, right? So it's actually punishing the dishonest behavior. So in this way, you can help at least reduce the risk of Oracle cheating. The same idea here. It's just a little bit of a convoluted, right? So here you give this turbo, right? So it says this UTXO has this amount and have this hash, has this script. So what do you do? If you can find a counter example, right? You push the transaction. You push a transaction that can prove. Then you can parse it and you say, oh, this UTXO coming from this transaction, but it has either a different amount or have a different script. And then I can know you are committing fraud, right? Then I can take this contract can be the condition. It's like you have now found a counter example that prove I've committing fraud. And then you can unlock the money here, right? You can take the deposit. That's a high level idea. You can think about it as 2 plus 2 equals 5. And then if you can prove this is false, then you can take the money. So that means that even using solution 1 without changing the pre-image hash is made even more secure. Again, it's not the holy grail we are looking for, but it's as far as it's the closest I've known.
I will build on this. Just an idea that came to mind when you're talking about this. Instead of just the bounty, we could modify the Oracle service that has to provide. It could be limited by the Merkle proof of the actual transaction and get a block header, like verify against the block headers. So that way you can have a proof of work parameter as well. I think the idea is you would take the transaction that was mined by the network, which means there's an SPV proof somewhere in those block headers, and then you could have it so that the Oracle signs the tuple, but then links it against that SPV proof somehow. I think we might be able to also attach not just a bounty, but a amount of energy expenditure on it. I think just an idea to build on this Oracle. I'm not sure where to take that, but I just want to mention I think there's a proof of work component we could attach for extra security.
Okay. Yeah, again, it's again, right? I think there's definitely, you can always have ways to increase the security. Basically, you push not only the signed turbo, right? You also push additional evidence, right? This is legit. You push, let's say, Merkle proof, right? The hearsay is bigger, but you are more confident, right? Of course, yes, that's a good idea. But there are also some cases I could say this may not work, right? For example, it's a chain of transactions, and the parents not mined yet, right? So you don't have a Merkle proof. So I'm saying you can add a security, but you can always reduce the level of trust. But the holy grail we are looking for is it possible theoretically to even completely get rid of this? Is treating the tokens as native satoshis. That's at least we talked. That's like $1 trillion question. Yeah.
I have well, I don't want to interrupt right now. If there's more you'd like to present, I just want to kind of start maybe talking about different approaches.
Yeah, that's not all I have to present. I mean, the rest is like we can just discuss. Yes.
So I have a question on on say for example, again, tokens. Let's go back to first minting of the tokens. So when we first mint the tokens, on what kind of data or what kind of connections do those tokens make back to the Bitcoin, the blockchain? So what exactly is that bridge that provides that, okay, the tokens were minted? I just want to, if there's a way we could start from there, and then let's continue going forward with moving the tokens and see where exactly do we need the where exactly do we need to actually where exactly the problem lies between that is, can we do that, or is that
I can also yeah, just on that. So let's say you're in the middle of a spend. Okay, you're spending a token, and you want to know that the parent came from the minting event. Well, one way is to know that the parent is the minting event, because there's all zeros in the first parameter. Let's say 36 bytes of zeros, and then so that's the blue box. When you mint, you could think of that as like the let's call that the token base, kind of like the coin base. There's a zero, there's a null input. So when you have that field set to 36 bytes, then the step 2, let's say any one of these, this first green box on the right to the blue, is checking, hey, because we have the parent out point, right, that we're spending. We say, hey, is that all zeros? Oh, it is. Okay, that's a minting event. So now let's embed in those place of those 36 bytes, let's embed the out point, the 36 bytes of the parent. And that's the baton in this article. There's that unique identifier that's being embedded in the step 2. And so then when you spend step 2 to the third transaction, you see, oh, it's not all zeros, which means we're definitely not at a minting event. It means we're in one of the middle steps. Okay, so now to go to the step 4, in order to know that we're not in the situation of the man in the middle attack, observe that it's not enough for just to look at our own parent. Because once again, you could just take any intermediate transaction after the mint, and you could just like put it into another TX, right? And then just claim it's authentic.
I think go back one step further. I think Samir, right? The reason we want to care about the genesis or the issuance or the, I don't know, you call it a good word, I call it token base, kind of like Coinbase, because how else would you identify, right? Let's say I have token A, right? How do I different from a token A plus? I can almost replay, right? I can take the same code. I can just create a parallel chain of transaction, right? How do you identify whether this transaction coming from A, not the fake one? You have to use some kind of unique ID, right? Unique token ID. So a good way is to use the out point, right? The TX ID plus the output. That's unique globally, right? So we use that as a token ID.
That's what's being embedded. Think of it like a baton, and we know it's globally unique because there's only ever one out point in the entire chain state in the UTXO set that could have ever had that out point. So we know that's globally unique, and then we can carry it along. Yeah. But then someone could copy an intermediate transaction, broadcast an intermediate step, an intermediate, like, one of these green boxes, and they just broadcast it fresh, basically spoofing and saying, oh yeah, I came from the original. So that's why when the code runs, we have to verify not just the parent, because that could just be a copy paste job. You have to verify the parent, because if you think about it, if you can verify that the parent and the parent share the same output contract code, then it's impossible for someone to copy in the middle of the chain, because the moment you try to spend it, you could never provide the grandparent transaction that conformed to the contract code. So it would actually basically be a dead token that's forever unspendable. And so by solving this induction process, we would basically allow anyone to know it's a real token, because they could just look back 2 steps and they see that it was spent. And that's irrefutable proof that it was valid by the laws of this token. But any spoof token would never hit your wallet, because no one could transfer it, because they could never provide the grandparent, because the grandparent was a forgery. That's the cool trick. Yeah, you can copy paste any intermediate step, and then I say, hey, send it to me, and you would like be physically unable to transfer it. It's like magic.
Using math, yes. Induction, yeah, that's the whole, is the counter example here, right? So if I can spoof, I can fabricate one, but what if I ask you to provide one step ahead? You cannot provide this because if it is a fake token, UTXO, here you cannot spend it, right? Because it requires two steps ahead. This all good, right? Because this one is not good. So the minus we reject here. So once you receive this, you know, parents good, by deduction, it's all good. So you can, so it's like your example, right? If I give you this dollar bill, right? You don't have to trace all the way. You somehow, I give you almost like a scanner, right? You can scan this. You don't even need to go back all the way. Who is using this dollar bill, right? You look at this, you can immediately tell whether it's legit or not. So that's a physical knowledge. What it can achieve, yes.
If we have some time, could we talk about the sig hash pre-image and the contents? If you could please pull that up, because, and then maybe it'll make it a little more concrete. Like there's the 10 steps in the, what's in the pre-hash, the pre-image. Yeah. Okay, so every transaction that you're unlocking context, you have the current pre-image of the current transaction. And observe you have number 2, the hash pre-vouts. So that's just the hash, but you can then also provide the actual vector of the pre-vout points being spent, and then you can hash it yourself, compare it to know that you have the pre-vouts. So you can get the parent, the parent input. And sorry, I just realized step 4 is that you actually already have the parent out point, but
special case, the one you are spending for
the one you're,
yes,
right. And so then we already know that the parent transaction contains the correct code, because look at number 5. The script code of the input is actually the output of the parent. So we already know that the parent is the same code that's running. And we know, remember the rule we said was that when you create a minting event with all zeros, then you must embed that out point along for the lifetime. So that's like a forward constraint. So if we can verify that the locking script is the same in the parent, then that's step 1, the base case of the induction. Step 2 is that, okay, does the parent of the parent also do the same thing in the locking script? If we can prove that step, then we prove the entire recursive relationship. And then it can only be spent if it goes back to the authentic minting event. So observe here that we already have the parent, enough information about the parent itself to know that the parent is good, but we don't have information about the grandparent, the parent of the parent. So the idea was, well, if we know what the out point is with step 4, then if we push the raw TX of the parent, then we can actually just parse the inputs of the raw TX, right, to get the grandparent TX ID. And then we can inspect the out point of that by pushing that onto the stack. That completes the step. But then each time you spend this transaction, you end up ballooning up, because you're always embedding on chain the raw TX of the parent and the grandparent. So that's when you get that Fibonacci explosion. So what I was thinking about in the past couple of days is, can we somehow create a chain of sig hash pre-images in such a way that we can create a relationship between an existing sig hash pre-image and its parent? So if maybe there's a way, observe number 8, hash outputs. We have the hash of the outputs of the current transaction. And then if we push the parent pre-image on, this is my line of thinking, if we have the parent's pre-image, maybe we can create some kind of a cryptographic or a signed relationship between the pre-images. So visualize a transaction. You have an input unlocking context on the left. And then when that transaction gets spent, you have another pre-image. So you're kind of like, there's a disconnect between the pre-images between the subsequent spends. But if we can create a logical connection going backwards from one pre-image to then derive the TX ID or some other identifier, right? So if we have the pre-image of the parent, and then we have, say, a hash of the grandparent, some kind of hash, maybe we can create a relationship going backwards. And in that case, then we could have irrefutable proof that we only need to push, say, at most 2 extra pre-images on the stack. And that would effectively become like a compressed a signature, like what BCH is doing, because we've established that relationship. I got a note from someone just a couple hours ago. I won't say who, because they're working on this, but they said they solved this, that it is actually possible to do this induction step. And they had the others look at it and they're writing it up. So this is a rumor. I don't know, because they didn't reveal anything to me, but they told me that it is possible. They spent a couple weeks and they solved it because of all this chatter that we had and the
No consensus change, right?
no consensus change.
Okay.
Correct.
Wow.
So I believe there is a solution out there. I don't know. Nothing was revealed to me other than this this teasing. But
Is it
if
the
it's true,
chain
it'll
of
be-
the chain of pre-images that's somehow hashed?
that was my idea. This person never revealed anything to me whatsoever. I read the messages multiple times. They did not give me a clue, and they said they'll have a paper published on this within a couple months, and it will be
Couple months.
released. And I said, oh, okay, well, we better solve it in parallel.
Okay, man.
It's chain of pre-images with the addition of transaction, the fresh transaction ID, probably. Yeah. And
Hey, Samir, do you know what recursion is? Because I think I had a moment where it all clicked of what you're trying to do. But do you know what the term recursion is in computer science?
yeah.
Yes or no? You do or no? I mean, it's okay if you don't. It's kind of an obscure topic. But when you do recursion, you're calling first you set like some parameters to where you'll exit this condition, but then you just call the function over and over, and you call it like it calls itself. And so my interpretation of this is if you can just go back like a couple things and all these conditions are set, then you could you use the word recursion, but you can go all the way back and see if this goes all the way back to the base condition. And then it all clicked to me of what we're trying to solve for. But then I realized maybe you don't know what recursion means, and that's why it's confusing. So I don't know.
I'd like to jump in with just another discussion point. Hopefully someone here or listening to this, maybe this sparks some ideas. Some interesting things we can do is with that inter-contract calling mechanism that you published on the sCrypt blog.
Okay, keep going. I open this.
Yeah, and so the idea I was thinking is that, well, what if you don't have to include the parent in the current lineage, but you can have like a parallel transaction chain. Think of them like brother and sister kind of working together, but they both have to be spent together. But somehow maybe one of them will have the parent history, the parent transactions, or the witness, will say, of what the parents are, and then the other will actually be the NFT. But together they have to be spent either together or in parallel, so that you always have like a dual track. And this is what I was thinking when you have this caller and callee relationship, where maybe one of the contracts solves for the parent, provides the hash into the output, and because you share the same output when you merge them together, you could extract the result into the other contract. Now, what I realized the problem with this is, if you look at the caller, you have to pass the raw.
Yeah, it's here. It's not here, right? It's here. Right. So you're kind of like doing the counting too, right? So, but it says again, same. It's in the same transaction though. So that's why I think I had the same idea. That's right.
And you have to provide the raw TX to the other.
Yeah. So if somehow you can cut this, but then you cannot communicate, right? So that's the dilemma. Basically, you put it in one transaction, so you can communicate, right? You can callee, but if you put it in one transaction, you just merely shift the raw transaction from the second input to the first input, right? But if you don't put it in the same transaction, then you cannot communicate. So that's kind of dilemma. But I don't know, maybe like a SIG hash. Somehow you can use SIG hash flags to that's another idea. Yes, I think I had the same idea. Yeah.
I have a question.
Sorry, go ahead.
So when you're spending these new minted tokens, do we also spend some form of Satoshis, the native tokens, on chain?
Doesn't have to, right? It's just to.
It doesn't have
it's
to?
independent. You can. So basically, when you represent the token, right, you have two information, right? One, who's the owner. Second, how many, right? If we're talking about fungible one, right? So how many tokens? You can either put in the Satoshi amount. I think that's what Stars token is doing, or you can put in script part, right? So output, you have two parts, right? Amount and also locking script. So you can use the Satoshi amount to denote how many tokens in this UTXO, or you can put the Satoshi, no, the token amount in the script as well, right? So that you decouple. Doesn't matter how many Satoshis you have. If you have one Satoshi, you can denote 1,000 tokens, or if you use stars token, one Satoshi is one token, right? It's independent. It depends on how you implement the tokens. Make sense?
Yeah, yes, that makes sense. But when it comes to the transaction being included in the on-chain, doesn't it need to have some kind of minor fee for which you are spending this?
Yeah.
The
It's
Satoshis?
Bitcoin transaction, right? It's like
Yeah.
another Bitcoin transaction. Yes, you have to pay the fees.
Yes. So that basically connects the, so doesn't that connect to these new tokens? Because every time you spend it, you have to have some kind of connection back to the the Bitcoin transaction chain, and because of the way we could trace the Satoshis, you can also do the same for the new non-fungible token. So is that I mean, does that make sense? Or yeah.
No, that's a separate issue. One is the token logic, right? The other one is how to pay the fees. You can come in from the token users yourself, or you can always supply additional inputs to cover the, and also additional change output, right? So here, this is a simplified, basically one input, one output. But in production, you most likely have more inputs here to cover the cost of a transaction fee and have one change output here. But that's I would say that's an orthogonal issue, independent of this. So these are additional inputs, outputs, you cover the fees, but that doesn't change the scope of problem here. Do you see what I mean?
It's kind of like they're
Yeah.
trying to resolve they're trying to design an overlay network.
Yeah,
And
okay.
yeah, you have to do these fees and stuff. But what we're just talking abstractly, I think, about what's the architecture of this overlay network.
Yeah, I think that makes sense. So basically, within the the token itself, there will be multiple inputs, and you're trying to figure out a way to validate that these multiple inputs are also valid and so forth. Yeah, makes sense. I think now I see the problem.
Okay.
Cool. Was it till like, I know you might have some stuff to say, but you got cut off a bunch.
Another idea, just to put out there, and these are just half-formed thoughts, but I just want to put them out for discussion, is we have this opcode separator, opcode, and just a quick review for everyone. What opcode separator does is when you use that opcode, the signature algorithm will preclude all the scripts before that opcode separator. Think of it like a scissors that snips an output, and it actually uses scissors, and it basically ignores everything to the left. So when the signature algorithm is run, like what's checked with checksig, it ignores everything to the left. And why you would do this is, for example, you might create a transaction where there's like a lot of data. I think the Netflix movie example was used before, where you have a lot of data in the output, and then later on you want to validate that that the transfer happened, or then you could like still provide the transaction, but minus all that big bulky data, and then the signature algorithm would still match, like will still work to prove that you did sign that transaction. So using this idea is maybe we could like not like hide or like present data in an output where we could provide like the grandparent transaction or maybe some information about the grandparent in one of the outputs, and then we put that before an opcode separator, and then if we apply a signature over that pre-image, and if we use checksig or some ECDSA signature checking, we're not directly verifying that the TX ID of the parent and the grandparent line up, but maybe we have like we'll call it like a surrogate chain of signatures, a surrogate hash, and then we're hiding the parent's parent inside an output that we can then prune in the subsequent step of the induction process. That's as far as I got, because I think there might be something here, because then it prevents the bloat problem, because then you don't need to include the entire transaction to validate that the signature matched. You could remove it. But of course, if you remove data, it still changes the TX ID, which is why we then cannot rely on TX IDs. We have to create some kind of other surrogate hash chain, back to what you were talking about earlier about some kind of proof of history, some other hash chain that then we could reconstruct with checksigs, then going backwards. I'm going to toss that out there.
Yeah, just brainstorming. I think it doesn't matter. It doesn't have to be mature. Yeah, I think So yeah, the difficulty here, this only applies, as I mentioned here, right? This only applies to check sig. It doesn't apply to transaction ID, right? So I wish there was some like almost like a code separator you can put in the transaction so that when you calculate the transaction ID, you can exclude some part. Okay,
I'm
but here,
curious,
yeah,
is
this
this before the pre-image or after the pre-image? When is this when does this truncation happen?
so here, right? So if you coming back again, okay, let's look at this, right? So this is the pre-image. It only affects the fifth field, basically whether you cut, you truncate some part of it. So it's part of the pre-image actually calculating. So if you don't have this, you put the script code, right? Why it's called script code, not locking script? Because if you have code separate, it's not always the code, the locking script in total, right? So if you don't have code separator, the script code equals locking script, right? If you have, so you just everything, including itself, is pruned before it. You cut from here. This is a script code.
Okay, very good. That's interesting.
So it's just ask. Okay. I think you guys are talking about on Twitter. I think I said it. I said so two people claim it, right? So one is Shatters and also the Brandon. That is the mystery guy one of the two, or is the third person? Or you cannot.
I don't think he wants to say.
The people that say I
It's
can't
okay if
say
you don't.
it was let's just say it was a secret, and I hope that they actually solved it.
Yeah, I don't care who it is. I just, if they really solve it, yeah, I'm happy. Yes. But it will be interesting to see. That's almost like I wouldn't say Bitcoin reinvention, but that's huge. Yeah, that would be huge.
There's, you know, a lot of times with this kind of stuff, and I don't know totally because I don't understand this totally, but like, you know, people always say I found a way, and we have this false sense of competition, but there's always something wrong with it. You know what I mean? It's like if somebody invents an app that's similar to mine, I used to be so upset about it. They stole my idea, whatever. But then when you look at it, you're like, no, they messed it up here, here, and here. And this isn't what I want anyways. And so it's like everybody has their own unique kind of way of doing things. And just like I showed with all these dollar bills, like there's going to be room enough for a lot of different things, in my opinion. I don't know. But obviously you want to have the best, or at least I do. I want to have the best solution. And so I try not to get too discouraged if somebody else claims they have something. It's like, well, let me look at it. But just something to add.
I think like the proof of history, concept with the hash chain, and also adding the transaction ID for the native UTXO might do the trick for this based on what I'm hearing right now.
Okay.
Proof of history is pretty
Yeah,
that hash chain is pretty cool.
I haven't checked it out. Right now you talk about it. I have to check out Solana proof of history. I have to check.
Yeah, proof of history. Yeah, so basically it's the exact same thing. Like so from the point of any token minting, they just keep on adding a hash, SHA-256 hash on that token itself with all the inputs and outputs, and then basically add more. Like you can add more data with the native UTXO transaction ID or whatever data we want on as part of the hash, and then keep on keep on creating that whatever the recursive whatever you're mentioning. So yeah, so I think there's some information there. The proof of history can do the trick, but this is just my
Okay, yeah,
small knowledge. But yeah,
have to check. Yeah, maybe there's some way we can borrow some ideas from there. Maybe, yeah. But now you really raised my curiosity because I've not been looking into Solana. I mean the white paper too much, but now proof of history, at least I have to check it out. Have you read it?
I haven't read the whole white paper. That's I mean I did start it off.
Part. that
Yeah,
can
the proof of history part. Yeah, I've listened to the guy, the founder, a few times about the proof of history, because that sounded kind of interesting. So
okay.
I think there is something to use some of that information for this particular problem. I see it.
Okay.
And in addition to the transaction ID of the some kind of transaction information from the native UTXO that connects us back to the original chain, and the chain of the hashes within that NFT, the token itself and the proof of history. I think together those can form a solution for this one, but a lot more technical details need to be figured out. But from a high level, this is how I see it. There might be a way to solve this. But now, thanks guys, because now I see the problem, and I can now start thinking about the solution as
How
well,
to
which is
solve
really
it.
cool. Yeah.
The $1 trillion
Yeah.
at stake here, literally, not even.
Who can have the best token?
Yeah.
It's fun.
Well,
It's
it
a lot.
applies.
It's a fun
Not only
problem. I
token.
never even.
Yeah, not only tokens. But I'm saying, you solve this, not only token, right? You can solve a lot of other, I don't know, even logistics, right? You don't have to track all the way. Somehow you know the latest.
Yeah, true.
You know it's all legit. You don't
Yeah.
have to, even it
Yeah.
goes through like 50 other suppliers, warehouses. You only check the last one.
Yeah.
You know it's good.
Yeah, and also like not only the last one, but any of the hash in between, and with the latest, you should be able to figure out that it's come from the original. It doesn't have to be the parent or the grandparent. It can be any from the say for example, it has moved hand like billions of times. Any one of those, like in between, any one of the hash and the latest token, you should be able to with certain be able to verify that it's come from the original. So that is a possibility. Because I don't know, like when we first started this I want to talk about the stable coin. That was something that was kind of related to this one as well. Like have a stable coin minted for any transaction that happens on chain, like any transaction. So it's I call it stable coin, but just a token, a random token, minted as soon as new transaction happens. And I think this is something similar to like to that as well. So, but yeah, this is cool.
I think they've been working on this for a while. They have a much deeper understanding than we have, Samir. But now we understand it. So I get it from a high level, but I just again, like me, like I'm still working on some of these basics of inputs and outputs. But you used a lot of language that I remember from just computer science and logic. So it was fun.
Okay. Any other?
But
We could wrap it up. Yeah, I just want to. I think Attila, I want to mention. So the core of the issue in my mind is now we know the parents locking script, right? So the only thing we're missing is the parents locking script. That's the only thing we care, right? But the problem is how do you get it without relying on like external oracles, right? I think the naive way would be push the transactions, but then you have the bloating issue. Somehow, if we can decouple this without push the whole transaction, at the same time, we can still get the parents locking script. Then we solve the issue, right? That's only
exactly.
Yeah, that's
the only thing we need is if we can have a two-step chain that proves that the locking script is equal to the current one, linking through it's going to be through the prev-out. If we can chain that back with some kind of a proof, a separate hash chain, something to get the grandparent locking script and have irrefutable proof that belongs to the immediate parent, then we've solved it. And generally, we've solved this induction problem generally. So that's exactly it. That's exactly all. We don't need like the entire transaction. The only reason we needed the entire transaction is because we were using it naively to hash the raw bytes of the full transaction, and then simply just linking up the prev-out point to the hash of the raw TX. But we can't use the full raw TX because it ends up compounding, because that raw TX ends up going on chain in the lineage of the current token. So somehow we need to be able to compress that information so that we can still know that it came from that, but without relying on the entire raw TX.
Mm-hmm. Yeah. Okay. Yeah. That's for all of us, and also for whoever is watching this. This is the core of the issue. So see if you can solve it, or as somebody already claimed to have solved it. That would be, yeah, I'll be really interested to watch and see. Yeah.
Yeah, this will be the biggest invention since Bitcoin itself, for real.
Say it again.
This will be the biggest invention since Bitcoin itself was invented.
Yeah, I would. Yeah, yeah. Personally, I would agree. Yes, it's huge. It's huge. No, you can also count a push TX, right? It's similar scale, right?
Sure.
Yeah.
After op push TX.
Yeah. Or after sCrypt, or after whatever Kevin's video, or after Attila's, superset, whatever. Okay, it's huge.
Well, this is what I was saying.
You'll be in history.
There's
You'll be history. I was
always, yeah.
You'll be Bitcoin
There's
history.
always another thing.
Yeah.
There's always another thing. So as soon as they invent the newest iPhone that has the most advanced cellular antenna, whatever, it's like, okay, actually we could do this better, and then we do it better. And so there's always another thing. So
Yeah.
that's why I always say have fun in the journey. Joy's in the journey.
Yes, that's why we're in this industry, hopefully. Okay.
Yeah.
Any other closing thoughts?
That's fun, guys. Thanks.
Okay. I think Attila, maybe it's your video freezes, but anyway, so we can safely call it a day, and we publish this, and hopefully more people can help think about this issue. Okay, see you, gentlemen. Have the Good Friday and weekend. So okay.
I think Attila's coming right back, so you can say about him.
Okay,
we're just closing up, Attila.
Yeah,
Any
I just got
closing
dropped by accident. Thanks
Okay.
for the. I don't have any closing thoughts, but I just want to thank everyone for participating, and the viewers as well to help us solve this problem.
Okay, you'll be in Bitcoin history. Whoever solved this, for sure. That's one for sure. Okay, see you guys. Enjoy your weekend. Okay.
See ya.
See everyone.
You too. Bye.